Today we will study the relationship between the Fourier series expansion and the Fourier transform. So firstly, consider this periodic signal. Any periodic signal can be expanded by the Fourier series. At here, Ck is called Fourier series coefficient, and the Ck defined by these equations. We taking integration over one period and divide by the period, and xt times e to the minus jk omega 0 t. This means the kth harmonic component. Omega 0 is this one. Omega 0 is the 2 pi over period. This t is the period. Okay, 2 pi over the t is called the period. So k omega 0 means kth harmonic component of them, and taking integration over the one period, it will give the ck. If we taking t goes to the infinity, then the signal becomes now a periodic signal. It's not periodic anymore. In a periodic signal, we define Fourier transforms. Okay, from here, what is the relationship between the Fourier series coefficient and the Fourier transform? The green part, this part, is defined in the Fourier transform. As t goes to the infinity, omega 0 is defined by 2 pi over t. And this one is very small steps of frequency if t is a very large number. So we define that as the infinitesimal small frequency step. And that small frequency step times k, we know that k moving from minus infinity to infinity, then that's the continuous frequency component. By using this replacement from this one, we'll define the xj omega. Okay, this green part redefined xj omega. This is called Fourier transform. If t goes to infinity, then this becomes a minus infinity, and this one should be positive infinity. And xt times e to the minus jk omega 0, but the k omega 0 is defined by omega, so that's defined in that way. Then we can figure out the Fourier transform of this one. And periodic signal can be expanded in the Fourier series coefficient like this way. Ck is the Fourier series coefficient, and Ck, from this relationship we can find out this one related to the 1 over t times xj omega. You know that green part corresponding to xj omega. So 1 over t, from here you can see from here that 1 over t can be replaced by d omega of d phi, 2 pi, okay, like that. 1 over t can be replaced by this way. Then ck enter to here, then we can find out 1 over 2 pi is here, xj omega are given here, and e to the j omega t is this one, and the d omega are this one, and the summation replaced by the integrations. So this one is the inverse Fourier transform. So we call this one is a Fourier transform, but this one is called inverse Fourier transform. So we define the Fourier transform and inverse Fourier transform is closely related to the Fourier series coefficient. To further investigate the relationship between Fourier series and Fourier coefficient, I do the Fourier transform definition from here. You know what, that we define the Fourier transform like this way, but the Fourier series coefficient, if we multiply ck times t, we can see here that the ck times period of t are defined by this way. But we are taking the integration minus infinity to infinity, but here minus t over 2 to the t of t. But you can think about this one maybe minus t over 2. This one maybe t over 2. Basically, all the times, all the values are 0 after this point. So basically this integration are the same as this one except for this variable k omega 0. Okay, but we are just taking with respect to time both of them. So basically it's the same integrations. So the only difference is frequency terms, these terms, k omega, but this one is omega, continuous version. When we taking the Fourier transforms, it will show up these red lines. This one is continuous curve. Okay, then what is the Fourier series coefficient times t? That is just the sampling of that one with a frequency step of k omega 0. Every k omega 0, it is sampled okay, like that. The arrow means actually the corresponding to delta function. Anyway, this one will follow the curve of Fourier transform, but it's sampled every k times omega 0. What if we increase the t? Then this frequency step will be smaller. So that shows over here. The frequency step is larger, but if we increase the period of t, then the sampling time is shorter and narrow, like that. As t increasing, the sampling step, frequency step is smaller, like that. This one is this one. If we taking the infinity, then continuous sampling is possible. That's this one. So I hope that you have some idea what's the relationship between the Fourier series coefficient to the Fourier transform vector. Now look at a little more detail. Here is a xt signal, is a periodic one. It's a rectangular pulse train. Its period is t. So we can expand the signal into a Fourier series expansion. But the Fourier series coefficient can be found by these integrations. We taking just one period of the time, taking integration over here by producting these basis functions. And the signal is non-zero only between minus tau over 2 to tau over 2, only this part. So we just integrate between here. Then we just integrating, it will give a sinc function. You know that this one is 2j times sine. So dividing by 2j, then we can get this result. And we can further simplify by the definition of sinc function, pi times something. So 2 divided by 2 pi t 1 over t can be replaced by k over t times tau. The numerator is the same. Denominator also can be replaced in the k. You know that, I mean that the k times pi first, 5 times. This one is k over t times tau. So this part, this one, pi is added here, the same for the numerator and denominator. So anyway, we can find out the Fourier series coefficient for this rectangular. The amplitude is 1. What if we taking t equals to the infinity? Then the periodic signal becomes the aperiodic now. So amplitude 1 is non-zero only between minus tau over 2 to tau over 2. So we taking the integration from infinity to the minus infinity, but all the way 0. So we just the integration over here. It's the same things. Okay. Then we can get this result. The difference is the k omega 0 are replaced by the omega. Then it will give this result, and also the numerator gives 2 times j sine. So we can replace that one into this way. So this is another sinc function. Now compare between the Fourier series coefficient and the Fourier transform value. From here, if you multiply t left hand side, then the remainder part you can compare. Tau is the same as this one, and k omega 0 are omega. Okay, then it's exactly the same. So that's why c times Fourier series coefficient times t0 are equals to x times j k omega 0. You know that this means that that's the sampling of this one. At every k omega 0 sampling will give the Fourier series coefficient value. And also we can express that one into a sinc function. Then the k over t corresponded to frequency. So think about it. So 1 over t corresponding to fundamental frequency. So if it taking the t goes to the infinity, the frequency step is very small. So multiplying k, that is the continuous version of the f. So I hope that you have some idea how to understand the Fourier series coefficient and the Fourier transforms. In previous class, we talked about that if a frequency domain, the Fourier transform has a k times delta omega minus omega 0, that plotted over here, it has only non-zero frequency component at omega 0, but it has delta function scaled by k times. Then by taking the inverse Fourier transform, you know that this part is xj omega. Okay, then we can taking the inverse Fourier transform, then we can have a time domain expression for that. So by taking integration of this one by use of delta function is only non-zero if omega equals to omega 0. So we can replace omega with omega 0. Then it gives a k over 2 pi times e to the j omega t. So this is the Fourier transform pair. If a Fourier transform has a k times delta omega minus omega 0 at the frequency domain, in the time domain, it is a complex exponential function scaled by k over 2 pi. And complex exponential can be expressed by cosine and sine signal, so just the sinusoidal one. So sinusoidal component can be converted into a delta function, and delta function coefficient k and the k over 2 pi are related in such a way. Then in the previous topics, we talk about the rectangular pulse train. That is a periodic one. The period of is t. Then it can be expressed by the Fourier series coefficient like this one. Okay. Then we can taking the Fourier transform of the periodic signals. Okay, we would like to take the Fourier transform, then that will give a Fourier transform expression for the periodic signals. From here, we know that the complex exponential terms, you know that from here, complex exponential term will be give, I mean that e to the j omega 0t can be converted to frequency domain. Fourier transform will give 2 pi times delta omega minus omega 0. Okay, by use of these relationships, by use of this one, we can just replace this the complex exponential term with the delta function like that. So for given ck coefficient, this complex exponential can be transformed in the Fourier domain 2 pi times delta omega minus k omega 0. Okay, this one. And the inverse Fourier transform can be found by these expressions. Okay, this is that things. Then we can replace with xtj omega at here. Then it will give 1 over 2 pi and the sigma ck times 2 pi omega minus k omega 0 and taking integration over omega. Then you know that omega is only non-zero at the k omega 0, so we can replace omega with the k omega 0. Then it will give this one. This one is just the Fourier series. So from here we can understand that the Fourier transform of periodic signals. Periodic signal can be transformed into a Fourier transform. From here that the complex exponential term, as we know that the complex exponential terms, by taking the Fourier transform, it will give 2 pi times delta omega minus omega 0. By use of this transform pair, we can convert xt over t signal can be expressed by this one. Fourier series coefficient times 2 pi and the delta omega minus k omega 0. So we can find out how to transform the periodic signals from here. And the last one that I would like to emphasize is this one. If time domain has a delta function, it means scaled a and it's a delta function a delta t. Then by taking the Fourier transform this xt, it will give constant value of a. So if time domain has impulses the delta function, then spectral domain is constant over the all frequency component. Okay. Lastly, I would like to talk about the duality. This duality topic will revisit later. But at this moment, what does this mean? Think about that. Here shows a time domain signals. This one, left side is time domain. It means that this axis is time. The right hand side is a spectral domain. It's a frequency domain. Okay. first consider this time domain pulse shapes. It is unit 1 in between minus tau over 2 to the tau over 2. This width is tau. And the area amplitude times time space is tau. Tau times 1. Okay, so this is tau, the area of this one. All the other time is 0. We take a Fourier transform of this one. Then we know that by taking transform of this one, it will give these sinc functions. This one shows the area of this one is tau. Okay, and sinc functions. This sinc function can be expressed by the sign like this one, and if we replace f frequency with angular frequency omega, 2 pi f is omega. Okay, so if we are using angular frequency, it can be expressed in this way: omega times tau over 2 and omega times tau over 2. And this one is the frequency axis is 1 over tau. You know that f equals 1 over tau, then it goes to the 0. This one is the first now. And the radian angles, we have to multiply 2 pi. So this one is corresponded here. If omega is 2 pi over tau, then 2 pi over tau times tau over 2 will give pi of this argument. It becomes the pi that goes to the 0. So if you're taking Fourier transform of this rectangular one, it transformed in these domains. The angular frequency is the 2 pi over this time space. 2 pi over tau is the first null. If we are counting the frequency domain as f, we can divide 2 pi, so this becomes one of type. So think about this pulse shape is pulse width is tau. Okay, amplitude is equals to 1. Then the height is amplitude times time width. So a tau is this one. This is amplitude. Amplitude times time space gives this peak point. And the first null is determined by this distance. Time distance is tau, then 1 over tau is the frequency. At that point, it goes to the 0. The opposite side is symmetric. And if you're taking 2 pi, then we can get the omega expression for that. What about in the spectral domain? In the spectral domain, this one is amplitude, and the bandwidth is positive bandwidth. It is W1 over 2 minus W1 over 2. It's quite symmetric with the time domain expression, but at this moment, this one is pi. Then taking the inverse Fourier transform are shown here. By taking the integration, it will give this result. And we can interpret that one into a sinc function. Okay, this is the amplitude. This amplitude is actually taking the area of this one. Amplitude times the bandwidth is W. But this one means that the radian angle by divided by 2 pi will give these peaks. So when we have this spectral domain result, we counting on with omega axis. So the angular frequency is this one. So omega 1 is also angular frequency. In that case, this omega 1 W1 over 2 pi is this peaks. And the first null occurred when this becomes the pi. So t will be 2 pi over W1. So this one is the first null, 2 pi over W1, it corresponding this null time. So relationship between the time domain, rectangular pulse to frequency domain are quite similar to rectangular pulse shapes in the frequency domain to the time domain expression for that. So both of them of these one sinc functions, and the sinc function characterized by the maximum peak at t equals 0 and the first null positions. We have to characterize by these 2 points. So how these 2 points are related to this one and the area. The area related to this peak, the same as this one. This area related to here. This space is related to this first null. It's the same. The first null is related here. So this property is called the duality.